Hello everyone. Today we'll study how to solve systems of linear equations using matrices. First of all, let's review some high school problems. Solve each of the following systems of linear equations. First of all, what is a linear equation? A linear equation is an equation where each term in the equation must be a constant, a variable, or a constant times a variable. If an equation is a linear equation, then every term in the equation must be a constant, a variable, or a constant times a variable. In a linear equation, every term must be a constant, a variable, or a constant times a variable. If in an equation it contains exponent, radical, or a variable on the denominator, or two variables multiplied together, then the equation is nonlinear. If in an equation it contains exponent, radical, variable in the denominator, or two variables multiplied together, then the equation is not a linear equation. In our example here, they are both linear equations. They are both systems of linear equations. Now let's solve the first example. Let's solve the first problem. 2x plus 4y equal to 2. 3x plus 5y equal to 4. How do we solve the system of equations? Here we can try to use elimination method. We can try to eliminate one of the variable first, and then solve for the other variable. If I multiply the first equation by 3, then the first term will be 6x here. If I multiply the second equation by negative 2, the first term here will be negative 6x. And then when I add them up, the first term gets cancelled. That's called elimination method. We eliminate one of the variable first, and then solve for the other variable. Now, if I multiply first equation by 3, I have 6x plus 12y equal to 6. If I multiply second equation by negative 2, I have negative 6x minus 10y equal to negative 8. If I add the equation together, 6x get cancelled. What's left is 2y equal to negative 2. Then I can divide both sides by 2. I get y equal to negative 1. Then once I know y, I can substitute y into one of the equation and then solve for x. If I substitute y into the first equation, I have 2x plus 4 times negative 1 equal to 2. So 2x minus 4 equal to 2. 2x equal to 6. Divide both sides by 2. S equal to 3. So the answer is s comma y equal to 3 comma negative 1. Or we can write the answer as s equal to 3, y equal to negative 1. That's the answer to the first system of equations. Next example, 3x plus 4y plus z equal to 2. 2x plus 3y minus z equal to 7. X plus 2y plus z equal to 0. How do we solve this system of equations? We can use elimination method. Eliminate one of the variable first. If I add the first equation and the second equation together, what do I get? I have 5x plus 7y, z get cancelled, equal to 9. If I add the second and the third equation together, what do we get? I have 3x plus 5y, z get cancelled, equal to 7. Now we have two equations with two unknowns. I can solve an equation for x and y. Here, if I multiply the first equation by 3, I have 15x plus 21y equal to 27. if I multiply the second equation by negative 5, I have negative 15x minus 25y equal to negative 35. If I add the equation together, 15x get cancelled. 21y minus 25y is negative 4y. 27 minus 35 is negative 8. Then I can divide both sides by negative 4. I get y equal to 2. Once I know y, I can substitute y into one of an equation here and solve for x. If I substitute y into the first equation, I have 5x plus 7 times 2 equal to 9. 7 times 2 is 14. Subtract 14 from both sides. 5x equal to negative 5. And then divide both sides by x. Divide both sides by 5. X equal to negative 1. Once I know x and y, I can substitute x and y into one of the equation here and then solve for z. If I substitute x and y into the first equation, I have 3 times negative 1 plus 4 times 2 plus z equal to 2. Then I have negative 3 plus 8 plus z equal to 2. 5 plus z equal to 2. Subtract 5 from both sides. I get z equal to negative 3. So the solution to the equation is x, y, z equal to negative 1, 2, negative 3. Or we can write the answer as s equal to negative 1, y equal to positive 2, z equal to negative 3. Next, before I show you how to use matrices, let's redo the previous problem using a new technique. This new technique is very similar as the elimination method. For the new technique, I first of all call the equation in the first row R1 and call the equation in the second row R2. For the new technique, first step, I try to make the leading coefficient to be 1. How do I make 1 here? In order to make 1 here, I can divide the first equation by 2. Dividing by 2 is the same as multiplying by half. So I multiply first equation by half. Multiply equation in the first row by half. What do I get? If I multiply first row by half, I keep the second row the same. So multiply first row by half. Half times 2 is 1. Half times 4 is 2. Half times 2 is 1. That's my new equation in the first row. Equation in the second row stays the same. Next, I try to eliminate x in the second row. What can we do here? Here, we can try to multiply the first equation by negative 3 and then add it to the second equation. It will cancel 3x here. So what I can do is I multiply equation in the first row by negative 3 and then add it to the second row. I multiply the first equation by negative 3 and then add it to the second equation. What do I get? So here, first of all, I leave the first equation the same. That's my R1. Then I multiply this equation by 3. I get negative 3. I multiply this equation by negative 3. I get negative 3x minus 6y equal to negative 3. And then add it to the second row. Equation in the second row is 3x plus 5y equal to 4. If I add them up, 3x cancel. Negative 6y plus 5y is negative 1y equal to 1. So the new equation is negative 1y equal to 1. That's my new equation in the second row. That's my new equation in row 2. Next, we can try to solve for y. How do we solve for y here? In order to solve for y, we try to make the coefficient of y to be 1. So what we can do here is, I multiply the second row by -1. Multiply the equation in the second row by -1. If I multiply the equation in the second row by -1, equation in the first row stays the same. Equation in the second row become y equal to -1. If I multiply the equation in the second row by -1, I get y equal to -1. Here I get y by itself. That's equation in the first row, and that's the equation in the second row. Next, we try to solve for x. In order to solve for x, we try to eliminate this y in the first row. How do I eliminate this y in the first row? What I can do here is, I multiply the equation in the second row by -2, and then add it to the first row. It will cancel y. I multiply the equation in the second row by -2, and then add it to the first row. Multiply the equation in the second row by -2, and then add it to the first row. Here, equation in the second row stays the same. I multiply equation in the second row by -2, which means I make -2y equal to 2. I multiply equation in the second row by -2. I get -2y equal to 2. Then add it to the first row. First row is x plus 2y equal to 1. If I add them together, I get x equal to 3. So that's the new equation. That's the new equation in the first row. S equal to 3. That's the new equation in the first row. So the answer is sy equal to 3 comma -1. Or we can leave it the way it is. S equal to 3, y equal to -1. That's a new technique. Now, let's use a new technique for the second example. For the second problem, I can first of all call the equation in the first row R1, and the equation in the second row R2, equation in the third row R3. First of all, I try to make the coefficient in the first row to be 1. How can we make 1 here? Instead of dividing the first equation by 3, I can switch row 1 and row 3. If I switch row 1 and row 3, that's easier than dividing the first row by 3. So I can switch row 1 and row 3. Interchange row 1 and row 3. Let me use capital R's. If I interchange row 1 and row 3, I have x plus 2y plus z equal to 0. That's my new R1. That's my new row 1. 2x plus 3y minus z equal to 7. That's my new row 2. 3x plus 4y plus z equal to 2. That's my new row 3. I interchange row 1 and row 3. I make 1 here. Next, I try to eliminate x in row 2 and row 3. How do I eliminate x in row 2 and row 3? First of all, let me eliminate 2x in row 2. In order to eliminate 2x in row 2, I multiply the first equation by -2 and then add it to the second equation. I multiply the first equation by -2 and then add it to the second equation. I first of all leave the first equation the same. X plus 2y plus z equal to 0. I multiply the equation in the first row by -2 and then add it to the second row. What do I get? multiply equation in the first row by negative 2, I have negative 2x minus 4y minus 2z equal to 0. Second row is, equation in the second row is 2x plus 3y minus z equal to 7. If I add them up, 2x can cancel. Negative 4y plus 3y is negative y. Negative 2y plus negative y is negative 3y. So negative 2z plus negative z is negative 3z. 0 plus 7 is 7. So that's a new equation in the second row. If I take negative 2 times row 1 plus equation in row 2, I get negative 3 plus 3 negative y minus 3z equals 7. That's a new equation in the second row. So what I did here is I multiply equation in the first row by negative 2 and add it to the second row. That's what I get here. That's a new equation in row 2. Next, how do I eliminate 3x here? All I can do is I multiply the first equation by negative 3 and add it to the third equation. I multiply first equation by negative 3, add it to the third equation. Multiply first equation by negative 3, add it to the third equation. I will eliminate this 3x here. If I multiply first equation by negative 3, I get negative 3x minus 6y minus 3z equal to 0. Plus the equation in the third row, that's 3x plus 4y plus z equal to 2. If I add them up, 3x cancel. Negative 6y plus 4y is negative 2y. Negative 3z plus z is negative 2z equal to 2. So I get negative 2y minus 2z equal to 2. That's a new equation in the third row. That's a new equation in the third row. Next, we have two equations here with two variables. Now in the second row, I try to make leading coefficient to be 1 here. How do I make leading coefficient to be 1? What I can do is I can multiply the second equation by negative 1. So multiply the second equation by negative 1. If I multiply the second equation by negative 1 and leave the rest the same, I have x plus 2y plus z equal to 0. That's the equation in row 1. Negative 2y minus 2z equal to 2. That's the equation in row 3. For equation in row 2, I multiply the equation in row 2 by negative 1. Multiply this equation by negative 1, I get y plus 3z equal to negative 7. That's the new equation in row 2. Next, I try to use this y to eliminate the y's in the first row and the third row. Next, I try to use this y to eliminate the y's in the first row and the third row. How do I eliminate this y here? I try to use the second equation to eliminate the y in the first row and the third row. What can we do here? I can multiply second row by negative 2 and then add it to the first row. I can multiply the second row by negative 2 and then add it to the first row. Then this 2y will be cancelled. I can multiply the second row by negative 2 and then add it to the first row. These 2y will be cancelled. If I multiply second row by negative 2, I get negative 2y minus 6z equal to 14. add it to the first row. First row is x plus 2y plus z equal to 0. If I add them up, I get x, 2y can cancel, minus 5z equal to 14. So that's my new first row. That's my new first row. X minus 5z equal to 14. That's the new row 1. Here I multiply second row by negative 2. Add it to the first row. That's my new row 1. Next, I try to eliminate y in row 3. I try to eliminate y in row 3. What I can do is I multiply second row by 2, by positive 2. Multiply second row by positive 2, and then add it to the third row. So I multiply second row by positive 2, and then add it to the third row. Multiply second row by positive 2, I get 2y plus 6z equal to negative 14. Add it to the third row. The third row is negative 2y minus 2z equal to 2. Multiply second row by positive 2. Add it to the third row. I have 2y can cancel. 4z equal to negative 12. So the third row is 4z equal to negative 12. That's my new row 3. That's the new row 3. Next, in the third row, we try to solve for z. That means I try to make the coefficient to be 1. In the third row, we try to solve for z. That means we try to make the coefficient to be 1. What can we do here? Here I can divide the third row by 4, which means multiply the third row by 1, 4. Multiply the third row by 1, 4, and leave the rest the same. X minus 5z equal to 14. Row 1 stays the same. Y plus 3z equal to negative 7. That's row 2. For row 3, multiply row 3 by 1, 4. If I multiply 4z by 1, 4, I get z by itself. If I multiply negative 12 by 1, 4, I get negative 3. That's the new row 3. Next, we try to eliminate the z's in the first row and the second row and get s and y by itself. Next, we try to eliminate z's in the first row and the second row and get s and y by itself. What I can do here is I can multiply the third row by 5 and then add it to the first row. It'll cancel negative 5z here. And then multiply negative 3 to the third row. Add it to the second row. It'll cancel 3z here. So I multiply the third row by 5. Add it to the first row. Multiply the third row by 5. Add it to the first row. First of all, I leave the third row the same. Then multiply the third row by 5. Add it to the first row. Multiply the third row by 5. I get 5z equal to negative 15. First row is x minus 5z equal to 14. If I add them together, I get x equal to negative 1. 5z can cancel. So the new row 1 is x equal to negative 1. That's the new equation in the first row. I get x equal to the negative 1. That's the new equation in the first row. Next, I can multiply the third row by -3, add it to the second row. Multiply the third row by -3, add it to the second row. The third row is z equal to -3. If I multiply the third row by -3, I get -3z equal to 9. Second row is y plus 3z equal to -7. If I add them up, I get y equal to +2. That's a new equation in the second row. That's a new equation in the second row. Y equal to +2. That's a new equation in the second row. So here I get syz by itself. X is -1, y is 2, z is -3. So the answer is x, y, z equal to -1, 2, and -3. That's exactly the same as what we have in the beginning. Syz is -1, 2, and -3. So we get exactly the same answer using the new technique. Next, based on this new technique, I can show you how to solve the equations using matrices. First of all, rewrite the coefficient of an equation as the entries of a matrix. So I write the matrix as 2, 4, 2, 3, 5, 4. This is called the augmented. This is called augmented matrix of this system of equations. This is called augmented matrix of this system of equations. So first step, rewrite the equations as a matrix first. Next, we try to do matrix operation. First step, I try to make the first entry in the first row to be 1. First step, I try to make the first entry in the first row to be 1. Here I can divide the entire row by 2. I can divide the entire row by 2, which means multiply row 1 by half. Divide the first row by 2, which means multiply the first row by half. I get 1, 2, 1. And leave the second row the same. 3, 5, 4. Next, once I make 1 here, this 1 is called a leading 1. I try to make everything below leading 1 to be 0. How do I make 0 here? What I can do is I multiply the first row by -3, add it to the second row. Multiply first row by -3, add it to the second row. I leave the first row the same. Multiply first row by -3, add it to the second row. -3 times 1 is -3. -3 plus 3 is 0. -3 times 2 is -6. -6 plus 5 is -1. -3 times 1 is -3. -3 plus 4 is +1. That's the same as we have here. Next, in the second row, I try to make the first non-zero entry to be a 1. In the second row, I try to make the first non-zero entry to be a 1. What I can do is I multiply second row by -1. So I leave the first row the same. Next, that's a leading 1 in the second row. Let's call a leading 1 in the second row. Next, we try to make everything above leading 1 to be 0. try to make everything above or below leading 1 to be 0. All I can do is I can multiply the second row by -2 and then add it to the first row. Multiply second row by -2, add it to the first row. So leave the second row the same. Multiply second row by -2, add it to the first row. Number 1 stays the same. 1 times -2. 1 times -2 is -2. -2 plus 2 is 0. -2 times -1 is 2. 2 plus 1 is 3. That's exactly what we have here. Then for the final answer, run this matrix back as an equation. Run this matrix back as an equation. Entries in the first column represent x. Entries in the second column represent y. So if I write it back as an equation, I have 1x equal to 3. 1y equal to -1. That's an answer to this system of equations. So we get exactly the same answer using matrices. For the second equation, if we try to solve an equation using matrices, first of all, rewrite the equation as an augmented matrix first. So rewrite the coefficient as the entries of matrix first. I have 3, 4, 1, and 2. Second row, 2, 3, -1, and 7. Third row, 1, 2, 1, 0. Rewrite the coefficient as the entries of matrix first. Then, first step, we try to make the first entry in the first row to be 1. I try to make the first entry in the first row to be 1. All I can do here is I can interchange row 1 and row 3. If I interchange row 1 and row 3, I can make 1 here. So interchange row 1 and row 3. If I interchange row 1 and row 3, I get 1, 2, 1, 0. Second row stays the same. 2, 3, -1, 7. Third row become 3, 4, 1, 2. That's called the leading 1 in the first row. Once I make the first entry in the first row to be 1, I try to make everything below leading 1 to be 0. So I try to make 0 here and 0 here. How do I make 0 here? All I can do is I can multiply first row by -2 and then add it to the second row. I can multiply first row by -2 and then add it to the second row. Multiply first row by -2 and then add it to the second row. So I leave the first row the same. Multiply first row by -2, add it to the second row. -2 times 1 is -2. -2 plus 2 is 0. -2 times 2 is -4. -4 plus 3 is -1. -2 times 1 is -2. -2 plus -1 is -3. -2 times 0 is 0. 0 plus 7 is 7. Next, I try to make the entry in the third row to be 0. Everything below leading 1 must be 0. How can I make 0 here? What I can do is I can multiply first row by -3 and then add it to the third row. Multiply first row by -3, add it to the third row. I get 0. -3 times 1 is -3. -3 plus 3 is 0. -3 times 2 is -6. -6 plus 4 is -2. -3 times 1 is -3. -3 plus 1 is -2. -3 times 0 is 0. 0 plus 2 is 2. Then Let's move to the second row. In the second row, we try to make the first non-zero entry to be 1. In the second row, we try to make the first non-zero entry to be 1. What I can do here is I can multiply second row by -1. Multiply second row by -1. So first row stays the same. Multiply second row by -1. I get 0, 1, 3, -7. Leave the third row the same. 0, -2, -2, and 2. Next a leading 1 in the second row. We try to make everything above or below leading 1 to be 0. Once I found a leading 1, I try to make everything above or below leading 1 to be 0. How do I make 0 here? In order to make 0 here, I multiply second row by -2 and then add it to the first row. I can multiply second row by -2 and then add it to the first row. Here I leave the second row the same. 0, 1, 3, and -7. Multiply second row by -2 and then add it to the first row. -2 times 0 is 0. 0 plus 1 is 1. -2 times 1 is -2. -2 plus 2 is 0. -2 times 3 is -6. -6 plus 1 is -5. And -2 times -7 is 14. 14 plus 0 is 14. Next, we try to make 0 here. In order to make 0 here, I multiply the second row by +2 and then add the second row to the third row. Multiply the second row by +2 and then add it to the third row. 2 times 0 is 0. 0 plus 0 is 0. 2 times 1 is 2. And +2 plus -2 is 0. Here I make 0 here. Next, 2 times 3 is 6. 6 plus -2 is 4. 2 times -7 is -14. -14 times 2. -14 plus 2 is -12. Next, move to the third row. In the third row, we try to make the first non-zero entry to be 1. That's a leading 1 in the third row. So try to make the first non-zero entry to be number 1. Here I can divide the third row by 4, which is the same as multiplying the third row by 1/4. Then everything else stays the same. First row stays the same. Second row stays the same. Divide the third row by 4. I get 0, 0, 1. -12 divided by 4 is -3. That's the leading 1 in the third row. Next, we try to make everything above or below leading 1 to be 0. That means I need to make 0 here and 0 here. In order to make 0 in the first row, I multiply the third row by 5 and then add it to the first row. Multiply the third row by 5, then add it to the first row. I first of all keep the third row the same. Multiply the third row by 5, add it to the first row. 5 times 0 is 0. 0 plus 1 is 1. 5 times 0 is 0. 0 plus 0 is 0. 5 times 1 is 5. 5 plus -5 is 0. 5 times -3 is -15. -15 plus 14 is -1. Next, we try to make 0 here. That means I need to multiply the third row by -3 and add it to the second row. Multiply the third row by -3. Add it to the second row. If I multiply the third row by -3, I have -3 times 0 is 0. 0 plus 0 is 0. Negative 3 times 0 is 0. 0 plus 1 is 1. Negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. I make 0 here. Continue. Negative 3 times negative 3 is 9. 9 plus negative 7 is positive 2. If I write this matrix back to the equation, the variable here is x, y, and z. So in the first row, I get 1x plus 0y plus 0z equal to negative 1. Second row, I get 0x plus 1y plus 0z equal to 2. That means y equal to 2. In the third row, we have 0x plus 0y plus 1z equal to negative 3. That means z equal to negative 3. So here we can see that solving equations using matrices, we get exactly the same solution as we solve the equations without using matrices. But in general, for equations with more variables, solving equations using matrices will be much easier. And this technique here has a name. It's called a Gauss-Jordan elimination. It's called a Gauss-Jordan elimination. In order to study solve equations using matrices, next, let me give you some general introduction to matrices. Next, let me introduce dimension of a matrix. A matrix with n rows and m columns is called a m by m matrix. For example, in this matrix, the entries are A11, A12, A13, A1m, A21, A22, A23, A2m, A31, A32, A33, A3m, AN1, AN2, AN3, ANM. In this matrix, how many rows do we have? How many rows do we have? First row, second row, third row, n row. There are n rows. How many columns do we have? A11, A12, A13 until A1m. There are m columns. Here we can see that there are n rows, m columns. So the above matrix is a m by m matrix. Since there are n rows and m columns, this is a m by m matrix. In the previous example, this matrix, it has 3 rows and 4 columns. This is a 3 by 4 matrix. This is a 3 by 4 matrix. It has 3 rows. Because it has 3 rows and 4 columns, this is a 3 by 4 matrix. In an earlier example, this matrix has 2 rows and 3 columns. It's a 2 by 3 matrix. This is a 2 by 3 matrix. And in this matrix, Aij, what does Aij represent? Aij represent the numbers, which is also called an entry. Each number here is also called entries. It's also called an entry. Aij represent the numbers in the ith row and the jth column. Aij represent the numbers or the entries in the ith row, and the jth column. For example, A23 represent the numbers in the second row, third column. A23 represent numbers in the second row, third column. A31 represent the entries in the third row, first column. A31 represent the entries in the third row, first column. Next, let me introduce a special form of matrix called a reduced low echelon form. Consider the following properties of matrix. First property, for any rows in the matrix, the first non-zero entry is 1, which is called the leading one of the row. Look at these two matrices. The first non-zero entry is 1. The first non-zero entry is 1. They are called the leading ones. The first non-zero entry is 1. They are called the leading ones. Second property. The rows with all zeros are at the bottom of the matrix. The rows with all zeros are at the bottom of the matrix. Look at these two examples. The rows with all zeros are at the bottom of the matrix, so they both satisfy the second property. The third property. For any rows with leading ones, the leading one in the upper row is closer to the left. For any rows with leading ones, the leading one in the upper row is closer to the left. For any rows with leading ones, the leading one in the upper row is closer to the left. The leading one in the upper row is closer to the left. So they both satisfy property number 3. Property number 4. For every leading one in the matrix, all entries above or below the leading one are zeros. For every leading one in the matrix, all entries above or below the leading one are zeros. For every leading one in the matrix, all entries above or below leading one are zeros. So this matrix satisfies property number 4. For all leading one in the matrix, all entries above or below leading one are zeros. So this matrix satisfies property number 4. But this matrix doesn't satisfy the property of number 4. This is a leading one. The entry above leading one is not 0. This is a leading one. The entry above this leading one is not 0. So this matrix doesn't satisfy property number 4. Property 4 star. This is a weaker property of property number 4. It says, for every leading one in the matrix, all entries below the leading one are 0. Property number 4 says, entries above or below leading one. Property 4 star only says entries below the leading one. So 4 star is a weaker statement. It says, for every leading one in the matrix, all entries below the leading one are zeros. Look at the second matrix here. For all leading one in the matrix, there are 3 leading ones. For all leading one in the matrix, all entries below leading one are zeros. Only below leading one are zeros. This matrix satisfies property 4 star. It doesn't satisfy property number 4, but it satisfies property 4 star. This is not leading one. Don't worry about this number. This is not a leading one. This number 1 is a leading one. This is not a leading one. So don't worry about this number. For every leading one, the entries below leading one are zeros. So this satisfies 4 star. If a matrix satisfies property 1, 2, 3, and 4, if a matrix satisfies properties 1, 2, 3, and 4, then we say the matrix is in a reduced low echelon form. First matrix satisfies property 1, 2, 3, 4. So we say this matrix is in reduced low echelon form. This matrix is in reduced low echelon form. Since it satisfies property 1, 2, 3, and 4. This is in reduced low echelon form. The second matrix doesn't satisfy property number 4. So this is not in reduced low echelon form. This matrix is not in a reduced low echelon form. In the earlier example, this matrix is also in a reduced low echelon form. In every row, the first non-zero entry is 1. It satisfies the first property. For any row in the matrix, the first non-zero entry is 1. And also, the rows with all zeros are at the bottom of the matrix. There's no row of all zeros, so you ignore the second property. We assume it satisfies the second property. It doesn't violate the second property. The third property, For any rows with leading ones, the leading one in the upper row is closer to the left. Here we can see that leading one in the upper row is closer to the left. And also, for every leading one in the matrix, all entries above or below leading one are zeros. For all leading ones in the matrix, all entries above or below leading ones are zeros. So this matrix satisfies property 1, 2, 3, and 4. This is in a reduced low echelon form. This matrix is in a reduced low echelon form. And same as this matrix is also in a reduced low echelon form. The first non-zero entry is 1. Leading 1 in the upper row is closer to the left, and all entries above or below leading 1 are zeros. It satisfies property 1, 2, 3, and 4. It doesn't violate property number 2. That means it satisfies all 4 properties, 1, 2, 3, and 4. This is also in a reduced low echelon form. If a matrix satisfies properties 1, 2, 3, and 4 star, then we say the matrix is in a row echelon form, not reduced. It's in a row echelon form. We write it as REF, row echelon form. If a matrix satisfies property 1, 2, 3, and 4 star, we say the matrix is in a row echelon form, such as this example here. It satisfies property 1, 2, 3, and 4 star. For every leading one in the matrix, all entries below the leading one are zeros. For all leading one in the matrix, all entries below leading one are zeros. This matrix satisfies property 4 star. So this matrix is in row echelon form. It's in a row echelon form, not reduced row echelon form, but it's in a row echelon form. And this matrix is in a reduced row echelon form. It automatically satisfies the property 4 star because property number 4 is a stronger statement. If we satisfy property number 4, it automatically satisfies property 4 star. So this is also in row echelon form. If a matrix is in reduced row echelon form, then it's also in row echelon form. Next, let's look at some simple examples. For each of the following matrices, determine whether it's in a reduced row echelon form, low echelon form, or neither. Part A. Let's check all 4 properties. First property says, for any rows in the matrix, the first non-zero entries must be 1. Here in the third row, the first non-zero entries is not 1. So it's not in a reduced row echelon form. Property 1 fail. It's not in a reduced row echelon form. And it's not in row echelon form, since property 1 fail. It's also not in a row echelon form. How about B? Let's check these 4 properties. First property says the first non-zero entries must be 1. On each row, the first non-zero entry is 1. So it satisfies the first property. How about the second property? Second property says the rows with all zeros are at the bottom of the matrix. Here, this row with all zeros is not in the bottom. So it doesn't satisfy property number 2. Therefore, it's not in reduced row echelon form. It's not in row echelon form, since property 2 fail. How about C? Let's check all 4 properties. The first non-zero entry is 1. On each row, the first non-zero entry is 1. So it satisfies property number 1. And property number 2 says the rows with all zeros must be in the bottom of the matrix. Since there are no rows with all zeros, it automatically satisfies property number 2. How about property number 3? Property number 3 says, for any rows with leading ones, the leading one in the upper row is closer to the left. Here it doesn't satisfy property number 3. Look at these 2 rows. In the second row and the third row, they both contain the leading one. But the leading one in the upper row is not closer to the left. The leading one in the upper row here is not closer to the left. So it doesn't satisfy property number 3. Since property number 3 fail, this matrix is not in reduced row echelon form, and therefore it's also not in reduced. It's also not in row echelon form. Since property number 3 fail. Next one. How about this matrix? Let's check all 4 properties. For each row, the first non-zero entry is 1, so it satisfies the first property. Since there are no rows with all zeros, it automatically satisfies the second property. And for each leading one, the leading one in the upper row is closer to the left, so it satisfies property number 3. How about property number 4? Property number 4 says, for every leading one in the matrix, all entries above or below the leading one are 0. This is a leading one, this is a leading one, this is a leading one. The entries above or below leading one, they are not all zeros. The entries above or below leading one, they are not all zeros. So it doesn't satisfy property number 3. Therefore, it's not in reduced row echelon form. How about row echelon form? Let's check property 4 star. Property 4 star says, for every leading one in the matrix, all entries below the leading one must be 0. Here we only check the entries below the leading one. So for the first leading one, the entries below leading one are zeros. For the second leading one, the entries below leading one are also zeros. For the third leading one, nothing is below, so it's also automatically true. So all entries below leading one are zeros. It satisfies the third property. It satisfies the property 4 star. So since it satisfies property 1, 2, 3, and 4 star, this is in a row echelon form. Part D is in row echelon form. What about part E? Let's check each property individually. On each row, the first non-zero entry is 1, so it satisfies the first property. Since there are no rows with all zeros, it automatically satisfies the second property. And the leading ones on the upper row is closer to the left, so it satisfies the third property. And all entries above or below leading one are zeros. It satisfies the fourth property. Since it satisfies property 1, 2, 3, and 4, this is in a reduced row echelon form. If a matrix is in reduced row echelon form, then it's automatically in row echelon form. So part E is in both reduced row echelon form and row echelon form. How about part F? Let's check all 4 properties. On each row, the first non-zero entry is 1, so it satisfies the first property. Since there are no rows with all zeros, it automatically satisfies property number 2. And also, the leading ones in the upper row is closer to the left. Leading one in the upper row is closer to the left. Then it satisfies property number 3. How about property number 4? The entries above or below leading one, they are not all zeros. Since the entries above or below leading one, they are not all zeros, it doesn't satisfy property number 3, so it's not in a reduced row echelon form. How about property 4 star? Let's look at the entry below the leading ones. Entry below leading one is 0. Entries below leading one are also 0 here. Since all entries below leading one are zeros, it satisfies property 4 star. So this is in a row echelon form. It's in a row echelon form. Next, let me introduce 3 operations to reduce matrices. They are called elementary row operations. In order to solve a system of linear equations using argumentative matrix, we are allowed to use the following 3 operations. First operation, we are allowed to multiply a row by a non-zero constant. Second operation, we are allowed to interchange 2 rows. Third operation, we are allowed to multiply a row by a constant and then add the result to another row. These 3 operations, they are called the elementary row operations. In our earlier example, when we are solving equations using matrices, that's all operations we use. In the earlier example, when we solve this system of equations using matrices, that's the operation we use here. We interchange 2 rows. We multiply a row by a constant, add it to a different row. Multiply a row by a constant, add it to a different row. We multiply a row by a constant. That's all we use. And this operation on matrices, is equivalent to an operation on equations. Next, let's look at some simple examples. Reduce each of the following matrices to the reduced row echelon form using elementary row operations. Elementary row operations means these three operations. We're allowed to multiply a row by a non-zero constant. We're allowed to interchange two rows. We're allowed to multiply a row by a constant and then add a result to another row. They are called elementary row operations. First examples. We try to reduce a matrix to the reduced row echelon form. So in the first row, we try to make the first non-zero entry to be 1. How do I make 1 here? Of course, I can divide the first row by 2. The thing is, if I divide the first row by 2, it generates fraction. If I divide the first row by 2, I get 1 half negative 2, negative half, 11 over 2. If I divide the first row by 2, it generates fractions. And then if we reduce matrices using fractions, it will be very, very complicated. So in order to avoid fraction, how can I make 1 here? In order to avoid fraction, what can we do here? In general, we try to avoid fractions. But if that's the only choice, then we have to use fractions. In general, we try to avoid fractions. But sometimes we are not allowed, sometimes we cannot avoid fraction. In that case, we must use fractions. But here, can we avoid fraction here? Can I make 1 here without using fraction? Think of this. If I add the third row to the first row, it won't generate any fractions, and I can make 1 here. If I multiply the third row to the first row, if I add the third row to the first row, that means I multiply the third row by number 1 and then add it to the first row. That's the third operation. I multiply a row by a constant, add it to a different row. If I multiply the third row by 1, add it to the first row, the third row stays the same. Second row stays the same. Add the third row to the first row. Negative 1 plus 2 is positive 1. 0 plus 1 is 1. Negative 2 plus negative 4 is negative 6. Negative 4 plus negative 1 is negative 5. Negative 9 plus negative 11 is negative 20. I'll have a leading 1 here. Next, in the first row, I try to make all entries below leading 1 to be 0, since I want to answer in the reduced row echelon form. So once I find leading 1, I try to make all entries above or below leading 1 to be 0. In the second row, it's already 0. In the third row, how do I make 0 here? Here I can simply add the first row to the third row. So I add the first row to the third row. Here I can simply add the first row to the third row. So I leave the first row the same. Leave the second row the same. Add the first row to the third row. 1 plus negative 1 is 0. 1 plus 0 is 1. Negative 6 plus negative 2 is negative 8. Negative 5 plus negative 4 is negative 9. Negative 20 plus negative 9 is negative 29. Now we are done with the first row. Move to the second row. I try to make the first non-zero entry to be 1. In the second row, I try to make the first non-zero entry to be 1. How can I make 1 here? I can divide the second row by 3. If I divide second row by 3, it won't generate any fraction, the number becomes smaller. Or we can switch second and third row. Either way is okay. We have two choices here. We can switch second row and third row. Or I can simply divide second row by 3. In this example, dividing the second row by 3 is easier because I make the number smaller. So here I can divide the second row by 3. Dividing by 3 means multiply by 1/3. That's the second operation. We're allowed to multiply a row by a constant. Here I multiply second row by 1/3. If I multiply second row by 1/3, first row stays the same, third row stays the same. In general, write down the unchanged row first. Then multiply second row by 1/3. Then do an operation. Write down the unchanged row first, and do an operation. 0 times a third is 0. 3 times a third is 1. 0 times a third is 0. -3 times a third is -1. 9 times a third is 3. Now I find a leading one in the second row. Since I try to reduce the answer, reduce the matrix to reduce the echelon form. That's a leading one. I try to make all entries above or below leading one to be 0. So here I can multiply second row by -1, add it to the first row to make 0 here. And multiply second row by -1, add it to the third row to make 0 here. So here I can multiply second row by -1, add it to the first row. Here I multiply second row by -1, add it to the first row. Second row stays the same. Write down the unchanged row first. Multiply second row by -1, add it to the first row. 0 times -1 is 0. 0 plus 1 is 1. 1 times -1 is -1. -1 plus 1 is 0. -1 times 0 is 0. 0 plus -6 is -6. -1 times -1 is 1. 1 plus -5 is -4. -1 times 3 is -3. -3 plus -20 is -23. Next, I try to make 0 here. So I multiply second row by -1, add it to the third row. Zero times -1 is 0. 0 plus 0 is 0. -1 times 1 is -1. -1 plus 1 is 0. -1 times 0 is 0. 0 plus -8 is -8. -1 times -1 is 1. 1 plus -9 is -8. -1 times 3 is -3. -3 plus -29 is -32. Next, let's move to the third row. In the third row, we try to make the first non-zero entry to be 1. Since we try to run a matrix in reduced low echelon form, in the third row, we try to make the first non-zero entry to be 1. Here, there's no choice. The only choice for us is divide the third row by -a. The only choice for us is divide the third row by -a. So dividing the third row by -a is in a sense I multiply the third row by -1/a. That's the only choice we have. So write down the unchanged row first. Here, first row stays the same. Second row stays the same. Multiply the third row by -1/a. I get 0, 0, 1, 1, 4. That's a leading one. I try to make all entries above or below leading one to be 0. Here, this entry is already 0. So I try to make this entry to be 0. So here I can multiply the third row by +6, add it to the first row to make 0 here. Here I can multiply the third row by 6, add it to the first row. So second row and the third row stays the same. Write down the unchanged row first. Means these two rows stays the same. Write down these two rows first. Multiply the third row by 6, add it to the first row. 6 times 0 is 0. 0 plus 1 is 1. 6 times 0 is 0. 0 plus 0 is 0. 6 times 1 is 6. 6 plus -6 is 0. 6 times 1 is 6. 6 plus -4 is 2. 6 times 4 is 24. 24 plus negative 23 is 1. So let's answer in reduced row echelon form. We can check the answer. The first non-zero entry is 1. And there's no rows with all zeros. And the leading one in the upper row is closer to the left. All entries above or below leading one are zeros. This is in a reduced row echelon form. So that's an answer to part A. Now, part B. Let's reduce this matrix to reduced row echelon form. First step, in the first row, we try to make the first non-zero entry to be a 1. How do I make 1 here? If I divide the first row by 2, it generates fraction. We try to avoid fraction here. So all I can do here is I can interchange row 1 and row 2. I can interchange row 1 and row 2. If I interchange row 1 and row 2, I can make 1 here. I get 1, 2, 0, 2, 4, 3. The rest stays the same. 0, 0, 2, negative 1, negative 2, 3. Next, since this is a leading one, we try to make all entries above or below leading one to be 0. For the answers in the reduced row echelon form, all entries above or below leading one must be 0. So I try to make 0 here, make 0 here. What I can do here is I can multiply first row by negative 2, then add it to the second row. So first row stays the same. Multiply first row by negative 2, add it to the second row. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times 2 is negative 4. Negative 4 plus 4 is also 0. Negative 2 times 0 is 0. 0 plus 3 is 3. In the third row, we have 0 here, so leave it the same. In the fourth row, try to make 0 here. In order to make 0 here, I can add the first row to the third row. Add the first row to the fourth row. That's the third operation. That means I multiply first row by positive 1, add it to the fourth row. So here, take first row, add it to the fourth row. 1 plus negative 1 is 0. 2 plus negative 2 is also 0. 0 plus 3 is 3. Next, let's move to the second row. Try to make the first non-zero entry to be 0. Try to make the first non-zero entry to be a 1. Can I make 1 here? In the second column, can I make 1 here? It seems impossible, since all entries are 0. It seems impossible we can make 1 here. Let's move to the third column. Can we make 1 here? Here I can divide the second row by 3, which means multiply the second row by 1/3. That's the only choice we can use here. Divide second row by 1/3. Or I can multiply the third row by negative 1, add it to the second row, but that's too complicated. An easier way is multiply the second row by 1/3. 1, 2, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3. Next, that's the leading one. We try to make all entries above or below leading one to be 0. It's already 0 in the first row, so don't change it. We try to make 0 here and here, in the third row and the fourth row. In order to make 0 here, I can multiply the second row by negative 2 and then add it to the third row. In order to make 0 here, I can multiply the second row by negative 3 and then add it to the fourth row. So here, multiply the second row by negative 2, add it to the third row. First row stays the same. I get 0, 0, 0. Negative 2 times 0 is 0. 0 plus 0 is 0. Negative 2 times 0 is 0. 0 plus 0 is 0. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Then in order to make 0 here, I multiply the second row by negative 3. Add it to the fourth row. Here, negative 3 times 0 is 0. 0 plus 0 is 0. Negative 3 times 0 is 0. 0 plus 0 is 0. Negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. That's an answer in a reduced row echelon form. There's a leading one in every non-zero rows. And rows with all zeros are in the bottom of the matrix. Leading one in the upper row is closer to the left. Leading one in the upper row is closer to the left. And all entries below leading one are 0. All entries above or below leading one are zeros. That's in a reduced row echelon form. Next example. Solve each of the following system of linear equations using matrix. Part A. 2x minus 4y minus z equal to negative 6. X plus 2y plus 3z equal to 2. 3y minus 3z equal to 15. In order to solve an equation using matrices, let's first of all write down the augmented matrix first. Let's write down augmented matrix from the equations first. So here, the coefficient of x is 2, 1, and 0. Coefficient of y is negative 4, 2, and 3. Coefficient of z is negative 1, 3, and negative 3. And the constant is negative 6, 2, and 15. In the augmented matrix, the first column represents coefficient of x, second column represents coefficient of y, and the third column represents coefficient of z. Next, let's reduce the matrix to the reduced row echelon form. First step, in the first row, we try to make the first non-zero entry to be 1. How do I make 1 here? I can divide the first row by 2, but then it will generate fractions. In order to make it easier, I can simply switch the first and the second row. So interchange row 1 and row 2. I have 1, 2, 3, 2, 2, negative 4, negative 1, negative 6, 0, 3, negative 3, 15. Once I find leading one in the first row, next, try to make all entries above or below leading one to be 0. In the third row, it has a 0 already. So all we need is make 0 here in the second row. So here I can multiply first row by negative 2 and add it to the second row. Multiply first row by negative 2, then add it to the second row. Leave the first row the same. 1, 2, 3, and 2. Multiply first row by negative 2, add it to the second row. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times 2 is negative 4. Negative 4 plus negative 4 is negative 8. Negative 2 times 3 is negative 6. Negative 6 plus negative 1 is negative 7. Negative 2 times 2 is negative 4. Negative 4 plus 6 is negative 10. The third row stays the same. 0, 3, negative 3, 15. Now move to the second row. In the second row, we try to make the first non-zero entry to be a 1. How can we make 1 here? I don't want to divide the second row by a, because it generates two fractions here. It will be too complicated. I can multiply the third row by 3 and then add it to the second row to make 1 here. But still, the number may be too big. A simple way is I can divide the third row by 3. I can divide the third row by 3. Then interchange second and third row. So multiply the third row by 1/3. I have 0, 1, -1, and 5. The rest stays the same. 1, 2, 3, 2, 0, -8, -7, -10. Next, I can interchange row 2 and row 3 to make 1 here. Interchange row 2 and row 3 to make 1 here. Next, this is a leading one. I try to make all entries above or below leading one to be 0. How can I make 0 here? I can multiply second row by -2 and then add it to the first row. And I can multiply second row by positive a, add it to the third row. So I can multiply second row by -2 and then add it to the first row. Here, second row stays the same. 0, 1, -1, and 5. Multiply second row by -2, add it to the first row. -2 times 0 is 0. 0 plus 1 is 1. -2 times 1 is -2. -2 plus 2 is 0. -2 times -1 is positive 2. 2 plus 3 is 5. -2 times 5 is -10. -10 plus 2 is -8. Now in the third row, try to make 0 here. Here I can multiply the second row by positive a. And then add it to the third row. A times 0 is 0. 0 plus 0 is 0. A times 1 is a. A plus -a is 0. A times -1 is -a. -a plus -7 is -15. A times 5 is 40. 40 plus -10 is 30. Now move to the third row. In the third row, we try to make the first non-zero entry to be 1. In the third row, we try to make the first non-zero entry to be a 1. In order to make 1 here, the only choice for us is to divide the third row by -15. That's the only choice we have. So divide the third row by -15, which means multiply the third row by -1/15. Here we have the first two rows stays the same. 1, 0, 5, -8, 0, 1, -1, 5, 0, 0, 1, and -2. That's a leading one in the third row. Next, we try to make all entries above leading one to be 0. What I can do here is I can multiply the third row by -5 and add it to the first row to make 0 here. Then I can directly add the third row to the second row to make 0 here. So I first of all multiply the third row by -5. Add it to the first row. So the third row stays the same. Multiply the third row by -5. Add it to the first row. Here, -5 times 0 is 0. 0 plus 1 is 1. -5 times 0 is 0. 0 plus 0 is 0. -5 times 1 is -5. -5 plus 5 is 0. -5 times -2 is 10. 10 plus -8 is 2. Next, I try to make 0 here. I can directly add the third row to the second row. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus -1 is 0. -2 plus 5 is positive 3. So this is in the reduced row echelon form. The first row represents 1x equal to 2. Second row represents 1y equal to 3. Third row represents 1z equal to -2. So the answer is s equal to 2, y equal to 3, and z equal to -2. This technique is called Gauss-Jordan elimination. This technique is called Gauss-Jordan elimination. This technique is called Gauss-Jordan elimination. We run augmented matrix first, then reduce it completely to the reduced row echelon form. Find augmented matrix first, and then reduce it completely to the reduced row echelon form, and then find the variables. This technique is called Gauss-Jordan elimination. In the book, you also introduce another technique called Gaussian elimination. In the book, you also introduce another technique called Gaussian elimination. Next, let me redo the problem using the Gaussian elimination. It's very similar to Gauss-Jordan elimination. Next, let me redo part A. Using another technique called Gaussian elimination. That's another technique introduced in the book. For the Gaussian elimination, first step is the same. Run find augmented matrix for the system of equations first. First step, run the augmented matrix for the system of equations first. The augmented matrix is the same. First column represents coefficients of x. Second column represents coefficients of y. Third column represents coefficients of z. So run augmented matrix first. I have 2, -4, -1, -6, 1, 2, 3, 2, 0, 3, -3, 15. So first step, run augmented matrix first. For Gaussian elimination, first step, run augmented matrix first. Next, for Gaussian elimination, reduce the matrix to row echelon form. For Gauss-Jordan elimination, we reduce the matrix here to reduce row echelon form. For Gaussian elimination, reduce the matrix to row echelon form, not reduced, row echelon form. Reduce this matrix to row echelon form. So here what I can do is try to make the first non-zero entry to be 1. So here I can switch row 1 and row 2. If I switch row 1 and row 2, I have 1, 2, 3, 2, 2, -4, -1, -6, 0, 3, -3, 15. Next, that's the leading one. We try to make all entries below leading one to be 0, not above, only below. Make all entries below leading one to be 0. Here I can multiply first row by -2, and then add it to the second row to make 0 here. Third row has 0 already. So multiply first row by -2, add it to the second row. First row stays the same. 1, 2, 3, 2. -2 times 1 is -2. -2 plus 2 is 0. -2 times 2 is -4. -4 plus -4 is -8. -2 times 3 is -6. -6 plus -1 is -7. -2 times 2 is -4. -4 plus -6 is -10. The third row has 0 already, so leave it the same. Next, we try to make 1 here. In the second row, try to make the first non-zero entry to be 1. Here, I can try to divide the third row by 3, and then interchange the second and the third row. Multiplying the third row by 1/3 is in a sense dividing by 3. So leave the first row and the second row the same. I get 0, 1, -1, and 5. Next, I can interchange the second and the third row. I'm making the first non-zero entry to be a 1. Let's call leading one in the second row. First row stays the same. Second row is 0, 1, -1, and 5. Third row is 0, -8, -7, and -10. Next a leading one. For row echelon form, we try to make all entries below leading one to be 0. We don't care about what's above leading one. We try to make all entries below leading one to be 0. So all I can do here is I can multiply second row by A, add it to the third row. Multiply second row by A, add it to the third row. I leave the first row the same. Second row stays the same. Multiply second row by A, add it to the third row. A times 0 is 0. 0 plus 0 is 0. A times 1 is A. A plus -A is 0. A times -1 is -A. -A plus -7 is -15. A times 4 is 40. 40 plus -10 is 30. Next, in the third row, we try to make the first non-zero entry to be a 1. The only choice for us is divide the third row by -15. So take -1/15 times row 3. I get 0, 0, 1, and -2. The rest stays the same. This is in a row echelon form. There's a leading one on each row. On each row, the first non-zero entry is a 1. It's a 1. And there's no row with all zeros. The leading one in the upper row is closer to the left, and all entries below leading one are zeros. This is in a row echelon form. For Gaussian elimination, we first of all reduce the augmented matrix to row echelon form. This is in row echelon form. Next, for Gaussian elimination, rewrite this matrix back to equations. Rewrite this matrix back to equations. So first row is 1x plus 2y plus 3z equal to 2. The second row is 1y minus z equal to 5. The third row is z equal to -2. Rewrite the matrix, rewrite the augmented matrix back to equations. First column represents coefficient of x. Second column represents coefficient of y. Third column represents coefficient of z. Those are constants. Then solve the equation using backward substitution. Solve the equation using backward substitution. Substitute z here, solve for y. And then substitute y and z here, solve for x. That's called the backward substitution. So I first of all substitute z here, solve for y. I get y minus -2 equal to 5. That means y plus 2 equal to 5. Y equal to 3. Next, substitute y and z into the first equation. Solve for x. I have x plus 2 times 3 plus 3 times -2 equal to 2. X plus 6 minus 6 equal to 2. S equal to 2. So here I have S equal to 2, y equal to 3, z equal to -2. I get exactly the same solution. And this technique is called the Gaussian elimination. This technique is called the Gaussian elimination. So for Gaussian elimination, we first of all reduce augmented matrix to low echelon form, and then change it back to equation, then substitute backward, solve for y and z, solve for x and y. This is called Gaussian elimination. And for Gauss-Jordan elimination, we reduce an augmented matrix directly to reduce low echelon form, and then get an answer directly. Those are two techniques of solving system of equations using matrices. For Gaussian elimination, we have less work on matrices. And for Gauss-Jordan elimination, we have more work in matrices, but we can get an answer directly. So depends on the problem. Sometimes one is easier than the other one. But in general, in my opinion, Gauss-Jordan elimination in general is easier than Gaussian elimination. Part B, 3x1 minus x2 minus 11x3 plus x4 equal to a. 2x1 minus 2x2 minus 10x3 plus x4 equal to 10. Negative 2x1 plus 6x3 plus 2x4 equal to 2. In order to solve the equations using matrices, let's first of all write down an augmented matrix. For an augmented matrix, in the first column, we write down the coefficient of S1. That's 3, 2, and negative 2. In the second column, write down the coefficient of S2. That's negative 1, negative 2, and 0. In the third column, write down the coefficient of x3. That's negative 11, negative 10, and positive 6. In the fourth column, write down the coefficient of s4. That's 1, 1, and 2. In the last column, write down the constants, a, 10, and 2. That's an augmented matrix of this system of equations. Next, we use Gauss-Jordan elimination. Write the equations, reduce the matrices to the reduced low echelon form. So first of all, in the first row, we try to make the first non-zero entry to be a leading one. What can we do here? If I divide the first row by 3, it generates fractions. It makes the problem much, much harder. So if possible, we try to avoid fractions. Here, what we can do is I can add a third row to the first row. Negative 2 plus 3 will be 1 here. So if I add a third row to the first row, it generates leading one without fractions. So I can add a third row to the first row. If I add a third row to the first row, I get 1, negative 1, negative 5, positive 3, and 10. The rest stays the same. 2, negative 2, negative 10, 1, and 10. Negative 2, 0, 6, 2, and 2. Next, since this is a leading one, I try to make all entries below leading one to be 0. So here I can multiply first row by negative 2, add it to the second row. I get 1, negative 1, negative 5, 3, and 10. Multiply first row by negative 2, add it to the second row. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times negative 1 is 2. 2 plus negative 2 is 0. Negative 2 times negative 5 is positive 10. Positive 10 plus negative 10 is 0. Negative 2 times 3 is negative 5, is negative 6. Negative 6 plus 1 is negative 5. Negative 2 times 10 is negative 20. Negative 20 plus 10 is negative 10. Next, for the third row, I can multiply first row by positive 2 and add it to the third row. Multiply first row by positive 2, add it to the third row. 2 times 1 is 2. 2 plus negative 2 is 0. 2 times negative 1 is negative 2. Negative 2 plus 0 is negative 2. 2 times negative 5 is negative 10. Negative 10 plus 10. Negative 10 plus 6 is negative 4. 2 times 3 is 6. 6 plus 2 is 8. 2 times 10 is 20. 20 plus 2 is 22. Next, let's move to the second row. In the second row, the first non-zero entry is negative 5 here. But in the third row, the first non-zero entry is here in the second column. Since we want the leading one in the upper row is closer to the left, I need to switch the second and the third row. Since we want the leading one in the higher row closer to the left, I need to switch the second and the third row. So let me switch the second and the third row. Since this number is closer to the left, so I switch the second and the third row. First row stays the same. Zero, negative 2, negative 4, 8, and 22. 0, 0, 0, negative 5, and negative 10. Next, in the second row, we try to make the first non-zero entry to be a leading one. So I can divide the second row by negative half. Multiply the second row by negative half. If I multiply the second row by negative half, first row and the third row stays the same. I get 0, 1, 2, negative 4, and negative 11. That's a leading one. Since that's a leading one here, I try to make all entries above or below to be 0. Here, the entry below is already 0. I try to make this entry here to be 0. Here I can simply add the second row to the first row. Take row 2 plus row 1. If I add the second row to the first row, second row stays the same. Third row also stays the same. Add the second row to the first row. 0 plus 1 is 1. 1 plus negative 1 is 0. 2 plus negative 5 is negative 3. Negative 4 plus 3 is negative 1. Negative 11 plus 10 is negative 1. Now let's move to the third row. In the third row, we try to make the first non-zero entry to be 1. Here I can divide the third row by negative 5. If I divide the third row by negative 5, it's the same as multiplying the third row by negative 1/5. So the first and the second row stays the same. I get 1, 0, negative 3, negative 1, negative 1. 0, 1, 2, negative 4, negative 11, 0, 0, 0, 1, 2. That's the leading one in the third row. Next, we try to make all entries above or below leading one to be 0. So I try to make 0 here and make 0 here. For the first row, I can simply add the third row to the first row. If I add the third row to the first row, I leave the third row the same. I get 0, 0, 0, 1, and 2. Third row plus the first row. 0 plus 1 is 1. 0 plus 0 is 0. 0 plus negative 3 is negative 3. 1 plus negative 1 is 0. 2 plus negative 1 is 1. In order to make 0 here, I multiply the third row by 4 and add it to the second row. So here, 4 times 0 is 0. 0 plus 0 is 0. 4 times 0 is 0. 0 plus 1 is 1. 4 times 0 is 0. 0 plus 2 is 2. 4 times 1 is 4. 4 plus negative 4 is 0. 4 times 2 is 8. 8 plus negative 11 is negative 3. So that's the reduced low echelon form. This is the reduced low echelon form. But here, we can see that x4 is 2, but we don't find a simple answer for x1 and x2. x4 is 2, but we don't find a simple answer for x1 and x4. What can we do here? In this case, we write it back as equation first. Write the reduced Rayleigh form back as equation first. So first row can be rewritten as x1 minus 3x3 equal to 1. Second row can be rewritten as s2 plus 2x3 equal to negative 3. And the last row is x4 equal to 2. In the first row, if I isolate s1, I can write s1 as 3x3 plus 1. In the second row, if I isolate s2, I can write it as negative 2x3 minus 3. For the third row, there's nothing we can do, so leave it the way it is. So here we can see that s1, s2, they both depend on x3. If I let x3 equal to t, for example, if I let x3 equal to t, then the solution can be written as x1 equal to 3t plus 1. x2 is negative 2t minus 3. x3 itself is t. x4 equal to 2. And here t can be any real numbers. That's the general solution to this system of equations. There are infinitely many solutions. Since t can be any real number, there are infinitely many solutions. This is the general solution to the system of linear equations. This is the general solution. Since there are infinitely many solutions, this is the general solution to the system of linear equations. In this case, we can see that in the second column and in the first column, second column, and the fourth column, there's a leading one. In the third column, there's no leading one. So for the variables corresponding to leading ones, they are called leading variables. Note. For the variables correspond to leading ones, they are called the leading variables. Here, x1, s2, and s4, they correspond to leading ones. s1, s2, s4, s1, s2, s4, they are called leading variables. And the other variables are called free variables. In this example, x3, since there's no leading one in this column, x3 is called a free variable. In this example, x1, x2, and x4 are the leading variables. And x3 is the free variable. Because in the column of x1, x2, x4, there are leading ones. In the column of x3, there's no leading one. So s1, s2, s4, they are called leading variables. x3 is called a free variable. For the general solution, if there exist free variables for the general solutions, of the systems of equations, we set the free variables equal to different variables. In this example, x3 is a free variable. I set x3 equal to a different variable, say t, and then write the leading variables in terms of the free variables. We set the free variable equal to a different variable, and then write the leading variable in terms of the free variable. That's a general solution. Set the free variable equal to a different variable, and then write the leading variable in terms of the free variables. That's the general solution. Next example, 2x1 minus 6x2 plus x3 minus x4 minus 2x4 equal to 10. Negative x1 plus 3x2 plus 2x3 minus 7x4 plus 6x4 equal to 0. x1 minus 3x2 plus x3 minus 2x4 equal to 6. In order to solve the equation using matrices, let's first of all write down the augmented matrix. For the augmented matrix, in the first column, write down the coefficient of s1. I get 2, negative 1, and 1. In the second column, write down the coefficient of s2. I get negative 6, 3, and negative 3. In the third column, write down coefficient of x3. I get 1, 2, and 1. In the fourth column, write down coefficient of s4. I get negative 1, negative 7, -2. Next column, write down coefficient of S5. I get -2, 6, and 0. Last column is the constant, 10, 0, 6. This is an augmented matrix of the system of equations. The first column is the coefficient of S1. First column is coefficient of S1. Second column is coefficient of S2. Third column is coefficient of S3. Fourth column is coefficient of S4. And the fifth column is coefficient of S5. Next, use Gauss-Jordan elimination. Reduce this matrix to reduced row echelon form. So in the first row, I first of all try to make the first non-zero entry to be a leading one. How can I make one here? I can simply switch the first and the third row. So switch row 1 and row 3. I can make 1, -3, 1, -2, 0, and 6. Second row stays the same, -1, 3, 2, -7, 6, and 0. Third row is 2, -6, 1, -1, -2, and 10. Since this is a leading one, I try to make all entries below leading one to be 0. So I can simply add the first row to the second row, and then multiply first row by -2, add it to the third row. So here, I add the first row to the second row. I have 1, -3, 1, -2, 0, 6, 0, 1 plus -1 is 0, -3 plus 3 is 0, 1 plus 2 is 3, -2 plus 7, -2 plus -7 is -9, 0 plus 6 is 6, 6 plus 0 is also 6. Next, I multiply first row by -2, add it to the third row. -2 times 1 is -2. -2 plus 2 is 0. -2 times -3 is +6. 6 plus -6 is 0. -2 times 1 is -2. -2 plus 1 is -1. -2 times -2 is 4. 4 plus -1 is +3. -2 times 0 is 0. 0 plus -2 is -2. -2 times 6 is -12. -12 plus 10 is -2. Next, in the second row, I try to make the first non-zero entry to be a leading one. Here I can simply divide the second row by 3. So multiply second row by 1/3. The first row stays the same. The third row stays the same. In the second row I get 0, 0, 1, -3, -2, +2. And +2. This is a leading one. I try to make all entries above and below leading one to be 0. So here I can multiply the second row by -1, add it to the first row to make 0 here. I can directly add the second row to the third row to make 0 here. So next, I multiply the second row by -1, add it to the first row. So second row stays the same. 0, 0, 1, -3, 2, and 2. Multiply the second row by -1, add it to the first row. -1 times 0 is 0. 0 plus 1 is 1. -1 times 0 is 0. 0 plus -3 is -3. -1 times 1 is -1. -1 plus 1 is 0. -1 times -3 is positive 3. Positive 3 plus negative 2 is positive 1. Negative 1 times 2 is negative 2. Negative 2 plus 0 is negative 2. Negative 1 times 2 is negative 2. Negative 2 plus 6 is positive 4. Next, I can add a second row to the third row. If I add a second row to the third row, 0 plus 0. 0 plus 0 is 0. 0 plus 0 is 0. 1 plus negative 1 is 0. Negative 3 plus 3 is 0. 2 plus negative 2 is 0. 2 plus negative 2 is also 0. In the third row, there's no leading ones. So that's in a reduced low echelon form. Next, since we have three variables, since the leading variable is x1 and x3, for x1, x3, there's leading ones, and the rest are free variables. Since there are free variables, we have infinitely many solutions. So here the free variable is x2, x4, and x5. Let me first of all write the matrix back as equations first. In the first row, I have x1 minus 3x2 plus x4 minus 2x5 equal to 4. In the second row, I can write it as x3 minus 3x4 plus 2x5 equal to 2. In the third row, they are all zeros. There's no equation. Next, isolate the leading variable. I can write it as s1 equal to 3x2 minus x4 plus 2x5 plus 4. S2 equal to 3x4 minus 2s5 plus 2. Here, x2, x4, s5 are free variables. So for the general solution, I let x2 equal to t, let x4 equal to s, let x5 equal to r. Then for the general solution, I can write s1 equal to 3t minus s plus 2r plus 4. S2 equal to t. x3 equal to, this is x3. x3 equal to 3s minus 2r. 3s minus 2r plus 2. S4 equal to s. S5 equal to r, where t, s, r can be any real numbers. That's the general solution. This is the general solution. Since there are infinitely many solutions, this is the general solution to this system of equations. This is the general solution to this system of the equations. Next example, 3x1 plus 6x2 plus 2x3 plus 3x4 plus 7s5 equal to negative 2. 2s1 plus 4s2 minus x3 plus 2s4 plus 7s4 equal to 2. Negative 4s1 minus 8x2 plus x3 minus 4x4 minus 13s5 equal to 2. In order to solve the equation, use matrices. Let's first of all write down the augmented matrix first. So for the augmented matrix, the first column represents the coefficient of S1. That's 3, 2, negative 4. Second column represents the coefficient of S2. That's 6, 4, -8. Third column represents coefficient of S3. That's 2, -1, and 1. Fourth column represents coefficient of S4. I have 3, 2, -4. The fifth column represents coefficient of S5. That's 7, 7, -13. And the last column is the constants. -2, 2, and 2. Here, let's use the Gauss-Jordan elimination. Reduce this matrix to the reduced row echelon form. So in the first row, we try to make the first non-zero entry to be a 1. What we can do here is, I can add the third row to the first row, then multiply the first row by -1. I try to avoid fractions. So I add the third row to the first row. I can make -1 here. Then I can multiply the first row by -1. So I first of all add the third row to the first row. So the third row stays the same. And the second row also stays the same. Add the third row to the first row. -4 plus 3 is -1. -8 plus 6 is -2. 1 plus 2 is 3. -4 plus 3 is -1. -13 plus 7 is -6. 2 plus -2 is 0. Next, I can multiply the first row by -1. I get 1, 2, -3, 1, 6, and 0. The rest stays the same. 2, 4, -1, 2, 7, 2. Next, -4, -8, 1, -4, -13, and 2. Since this is a leading one here, I try to make all entries below leading one to be 0. So here I can take the first row multiplied by -2, multiply the first row by -2, and add to the second row. I can make 0 here. Multiply the first row by -2, add it to the second row. I can make 0 here. So here the first row stays the same. 1, 2, -3, 1, 6, and 0. Multiply first row by -2, add to the second row. -2 times 1 is -2. -2 plus 2 is 0. -2 times 2 is -4. -4 plus 4 is also 0. -2 times -3 is 6. 6 plus -1 is 5. -2 times 1 is -2. -2 plus 2 is 0. -2 times 6 is -12. -12 plus 7 is -5. -2 times 0 is 0. 0 plus 2 is 2. Next, I can multiply first row by 4 and then add it to the third row to make 0 here. Multiply first row by 4, add it to the third row. 4 times 1 is 4. 4 plus -4 is 0. 4 times 2 is 8. 8 plus -8 is 0. 4 times -3 is -12. -12 plus 1 is -11. 4 times 1 is 4. 4 plus -4 is 0. 4 times 6 is 24. 24 plus -13 is +11. 4 times 0 is 0. 0 plus 2 is 2. Next, in the second row, I try to make the first non-zero entry to be a 1. How can we make 1 here? If I divide the second row by 5, there's a fraction here. If I divide the third row by 11, there's a fraction here. We try to avoid fractions. So what we can do here is, I can multiply second row by 2, add it to the third row. I can make negative 1 here. And then multiply the third row by negative 1, I can make 1. And then switch the first and the second, switch the second and the third row, I can make 1 here. So I multiply second row by 2, and then add it to the third row. I try to make a leading 1 here. I multiply second row by 2, add it to the third row, I can make 1 here. I can make negative 1. And then multiply the third row by negative 1, I can make 1. And then switch row 1 and row 2. Switch row 2 and row 3, I can make leading 1 here. So multiply second row by 2, add it to the third row. First of all, the first row stays the same. Second row stays the same. Multiply second row by 2, add it to the third row. I get 0, 0, negative 1, 0, positive 1. 2 times 2 is 4. 4 plus 2 is 6. Next, I can multiply the third row by negative 1. First and the second row stays the same. I get 0, 0, 1, 0, negative 1, negative 6. Next, I can switch row 2 and row 3 to make leading 1 here. So first row stays the same. 1, 2, negative 3, 1, 6, 0. 0, 0, 1, 0, negative 1. Negative 6, 0, 0, 5, 0, negative 5, and 2. So that's a leading 1 in the second row. We try to make all entries above and below leading 1 to be 0. So here I can multiply second row by 3, add it to the first row. So the second row stays the same. 0, 0, 1, 0, negative 1, and negative 6. Multiply second row by 3, add it to the first row. 3 times 0 is 0. 0 plus 1 is 1. 3 times 0 is 0. 0 plus 2 is 2. 3 times 1 is 3. 3 plus negative 3 is 0. 3 times 0 is 0. 0 plus 1 is 1. 3 times negative 1 is negative 3. Negative 3 plus 6 is positive 3. 3 times negative 6 is negative 18. Negative 18 plus 0 is negative 18. Next, to make 0 here, I can multiply the second row by negative 5 and then add it to the third row. Here I get 0, 0. Negative 5 times 1 is negative 5. Negative 5 plus 5 is 0. 0. Negative 5 times negative 1 is 5. 5 plus negative 5 is also 0. Negative 5 times negative 6 is 30. 30 plus 2 is 32. Next, in the third row, we try to make the first non-zero entry to be 1. That's a leading 1 in the third row. So here I can divide the third row by 32. There's no other choice. Divide the third row by 32. That means multiply the third row by 1 over 32. Here I can make 1, 2, 0, 1, 3. First row, second row stays the same. 0, 0, 1, 0, negative 1, negative 6. Divide the third row by 32, I get 0, 0, 0, 0, 0, and 1. That's a leading 1 in the third row. Next, we try to make all entries above the leading 1 to be 0. So here I can multiply the third row by 18, add it to the first row to make 0 here. Multiply the third row by 18, add it to the first row to make 0 here. The third row stays the same, 0, 0, 0, there are 5 zeros. Multiply the third row by 18, add it to the first row, Okay, 1, 2, 0, 1, 3, 0. Next, I can multiply the third row by 6, add it to the second row. That's 0, 0, 1, 0, negative 1, 0. This is the reduced low echelon form. Now here, if we observe the third row, we can see that if I run the third row as an equation, in the third row we have 0 equal to 1. If I run the third row as an equation, I have 0 equal to 1. In the third row, here we have 0 equal to 1. Since 0 can never equal to 1, we can never make this statement true. This is always false. So there's no solutions. Since this is a false statement, we can never make this true. So for all x, for all s1, s2, s3, we can never make this statement true. This is a false statement. So we say this equation, this system of equation has no solutions. In a reduced low echelon form, if we obtain 0 equal to some constant, 0 equal to some non-zero constant, there are no solutions. This system of equation has no solutions. That's a very, very special case. In general, there are 3 cases when solving a system of linear equations. Case 1. For an augmented matrix in a reduced low echelon form or low echelon form, if there exists the same number of variables and non-zero rows, then there exists unique solution. For example, in part A, for an augmented matrix in a reduced low echelon form, we have 3 non-zero rows and 3 variables. If there exists the same number of rows, non-zero rows, and variables, then there exists a unique solution for S, Y, Z. So here we have 3 non-zero rows and 3 variables. Then there exists a unique solution for S, Y, and Z. That's the first case. Case 2. For an augmented matrix in a reduced low echelon form or low echelon form, if there exists more variables or more unknowns than the number of non-zero rows, then there exists infinitely many solutions. In example C and D. In example B and C. That's the augmented matrix in a reduced low echelon form. If there exists, here we have 3 non-zero rows and 4 variables. There are 4 variables. And in a reduced low echelon form, we have 3 non-zero rows. If there are more unknowns than equations, then we have infinitely many solutions. Here we have infinitely many solutions. As for every t, there's a solution for every t. So we have infinitely many solutions. If there are more unknowns, more variables than the number of non-zero rows, then we have infinitely many solutions. Case 3. For an augmented matrix in a reduced low echelon form or low echelon form, for an augmented matrix in a reduced low echelon form or low echelon form, if the last non-zero row is in the form of 0, 0, 0, 0 with constant 1, then the system of equations has no solutions. If the last row in a reduced low echelon form or low echelon form, if the last row is 0, 0, 0, 0 and 1, then the system of equations has no solutions. In example D, for the matrix in a reduced low echelon form or low echelon form, if the last row is in the form of 0, 0, 0, 0, 1, then there's no solutions because we can never make 0 equal to 1. For any variables, we can never make 0 equal to 1. Then there are no solutions. So if the last row is in the form of 0, 0, 0, 1, then there are no solutions. If the system of equations has a unique solution or infinitely many solutions, that means in case 1 and 2, if there is a unique solution or infinitely many solutions, then we say the system is consistent. then we say the system of equations is consistent. If it has no solutions, that's case 3. If it has no solutions, then we say the system is inconsistent. Then we say the system of equations is inconsistent. Next example, 2x1 plus x2 plus 2x3 equals 0. Negative x1 plus 2x3 equals 0. 5x1 plus x2 equals 0. In this system of equations, we can see that all constants on the right side are zeros. That's a very, very special case. Note, in a system of linear equations, if all constants on the right side are zeros, then it's called a homogeneous system of equations. It's called a homogeneous system of linear equations. In this example here, all constants on the right side are zeros. This is a homogeneous system. Next, let's solve this system. We solve the equation exactly the same way. We first of all write the equation as an augmented matrix first. Write it as augmented matrix first. First column represents coefficients of S1. Here we have 2, -1, and 5. Second column represents coefficients of S2, which is 1, 0, 1. Third column represents coefficients of x3, that's 2, 2, 0. Last column are the constants, 0, 0, 0. This is a homogeneous system. We solve it the same way. Try to reduce this matrix to the reduced low echelon form first. In the first row, we try to make the first non-zero entry to be a 1. How do I make a 1 here? Here I can add the second row to the first row to make 1 here. Add row 2 to row 1. So I leave row 2 the same. Leave row 3 the same. Add row 2 to row 1. -1 plus 2 is 1. 0 plus 1 is 1. 2 plus 2 is 4. 0 plus 0 is 0. Now in the first row, this is a leading one. We try to make all entries below leading one to be 0. In order to make 0 here, I can add the first row to the second row. And to make this 0 here, I can multiply the first row by -5, add it to the third row. So let me first of all add the first row to the second row. If I add the first row to the second row, first row stays the same. 1, 1, 4, 0 stays the same. 1 plus -1 is 0. 1 plus 0 is 1. 4 plus 2 is 6. 0 plus 0 is 0. Next, I can multiply first row by -5, add it to the third row. 1 times -5 is -5. -5 plus 5 is 0. -5 times 1 is -5. -5 plus 1 is -4. -5 times 4 is -20. -20 plus 0 is -20. -5 times 0 is 0. 0 plus 0 is 0. Next, in the second row, we try to make the first non-zero entry to be a leading one. It's already a leading one here. It's already a leading one. So I try to make the entries above and below the leading one to be 0. Here I can multiply second row by -1, add it to the first row, and then I multiply second row by 4, add it to the third row. Let me first of all multiply second row by -1, add it to the first row. So I leave the second row the same, 0, 1, 6, 0. Multiply second row by -1, add it to the first row. 0 times -1 is 0. 0 plus 1 is 1. -1 times 0 is -1 times 1 is -1. -1 plus 1 is 0. -1 times 6 is -6. -6 plus 4. -6 plus 4 is -2. -1 times 0 is 0. -1 times 0 is 0. 0 plus 0 is 0. Next, I can multiply second row by 4. Add it to the third row. 4 times 0 is 0. 0 plus 0 is 0. 4 times 1 is 4. 4 plus -4 is 0. Next, 4 times 6 is 24. 24 plus -20 is 4. 4 times 0 is 0. 0 plus 0 is 0. Next, in the third row, we try to make the first non-zero entry to be a 1. So here I can divide the third row by 4, which means multiply the third row by 1, 4. So the first row, second row stays the same. Divide the third row by 4. I get 0, 0, 1, 0. Now, that's the leading one in the third row. Since it's a leading one, I try to make all entries above and below leading one to be 0. So in the first row, I can multiply the third row by 2, add it to the first row. For this 6, I can multiply the third row by -6, add it to the third row, to the second row. So I first of all multiply the third row by 2, add it to the first row. The third row stays the same. It's 0, 0, 1, 0. Multiply the third row by 2, add it to the first row. I get 1, 0, 0, 0. Next, multiply the third row by -6, add it to the second row. I get 0, 1, 0, 0. That's the reduced echelon form of this matrix, of this argumentative matrix. Now here, since there are 3 variables, and we have 3 non-zero rows, that means there exists a unique solution. So there exists a unique solution. x1 equal to 0, x2 equal to 0, x3 equal to 0. So the solution is x1 equal to 0, x2 equal to 0, x3 equal to 0. Next example, 2x1 plus 2x2 plus 4x3 equal to 0. 5x1 plus 5x2 plus x3 equal to 0. 3x3 equal to 0. This is a homogeneous system of equations. We solve it the same way. Let's first of all write down the argumentative matrix first. The first column represents coefficients of S1. I have 2, 5, 0. Second column represents coefficients of S2. I have 2, 5, 0. Third column is a coefficient of x3. I have 4, 1, 3. And the last column is 0. Last column is the constants, which are all zeros. Now, let's reduce this matrix to the reduced row echelon form. First of all, I try to make in the first column, in the first row, I try to make the first non-zero entry to be a leading one. Here, I can divide the first row by 2, which means multiply half to the first row. I get 1, 1, 2, 0. Leave the rest the same. I have 5, 5, 1, 0, 0, 0, 3, 0. Next, that's a leading one in the first row. I try to make all entries below leading one to be 0. So here I can multiply first row by -5, add it to the second row. first row stays the same. I have 1, 1, 2, 0. Negative 5 times 1 is negative 5. Negative 5 plus 5 is 0. Negative 5 times 5 is negative 5 times 1 is negative 5. Negative 5 plus 5 is 0. Negative 5 times 2 is negative 10. Negative 10 plus 1 is negative 9. Negative 5 times 0 is 0. 0 plus 0 is 0. The third row stays the same. 0, 0, 3. Next, move to the second row. Try to make the first non-zero entry to be a 1, to be a leading 1. So in the second row, I can multiply second row by negative 1 over 9. Leave the first row and the third row the same. I get 0, 0, 1, 0 in the second row. The third row stays the same. Next, that's the leading 1. I try to make all entries above or below leading 1 to be 0. So here I can take the second row times negative 2, add it to the first row. And take the second row times negative 3, add it to the third row. I first of all leave the second row the same. 0, 0, 1, 0. Multiply second row by negative 2, add it to the first row. Negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 0 is 0. 0 plus 1 is 1. Negative 2 times 1 is negative 2. Negative 2 plus 2 is 0. Negative 2 times 0 is 0. 0 plus 0 is 0. Next, I multiply second row by negative 3, add it to the third row. Negative 3 times 0 is 0. 0 plus 0 is 0. Negative 3 times 0 is 0. 0 plus 0 is 0. Negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times 0 is 0. 0 plus 0 is 0. That's the reduced row echelon form of the matrix. Now here we can see that there are 3 variables, but we only have 2 non-zero rows. If there are more unknowns than the number of equations, there are infinitely many solutions. Then we only have 2 non-zero rows, but there are three variables, 3 unknowns. If there are more unknowns than the number of non-zero rows, it has infinitely many solutions. So let me rewrite this back as equation first. Let's first of all rewrite the matrix back as equations. First row I have x1 plus x2 equal to 0. In the second row I have x3 equal to 0. Here x1, x3 they are leading variables. x1 and x3 they are leading variables. We try to get a leading variable by itself. I have x1 equal to negative x2, x3 equal to 0. x1 and x3 they are leading variables because for x1 and x2 there is a leading 1 in the column. For x2 there's no leading 1. This is not leading 1. This number 1 here is not leading 1. So since for number 2 there's no leading 1, since for x2 there's no leading 1, x2 is called a free variable. So I let x2 equal to a variable, to a different variable, say t. Then the general solution is x1 equal to negative t, x2 equal to t, x3 equal to 0. That's the general solution to this homogeneous system of equations. That's the general solution to this homogeneous of linear equations. T can be any real numbers. That's the general solution to this homogeneous system of linear equations. Note, for any homogeneous system of linear equations, it's always consistent because x1 equals 0, x2 equals 0, and so on is always a solution of the system. For example, in example F, there are 3 variables, x1, x2, x3. If I let x1 equals 0, x2 equals 0, and x3 equals 0, 0, 0, 0 satisfies all 3 equations. So x1 equals 0, x2 equals 0, x3 equals 0 is a solution to this homogeneous system of linear equations. Since it always has a solution, it's always consistent. And this solution 0, 0, 0 is called the trivial solution. The solution S1 equals 0, S2 equals 0, and so on is called a trivial solution to the homogeneous system. In example E, the solution S1 equals 0, S2 equals 0, S3 equals 0. This is called a trivial solution to the homogeneous system of equations. And if there exists other solutions for a homogeneous system, if there exist other solutions, then they are called non-trivial solutions. For example, in F, we know that there are infinitely many solutions. If I let t equal to 1, I have s1 equal to negative 1, x2 equal to 1, x3 equal to 0. Then the solution negative 1, 1, and 0 is a non-trivial solution to the homogeneous system of linear equations. So any solution other than 0, 0, 0 is called a non-trivial solution to the homogeneous system. Also, since the homogeneous system is always consistent, then either it has only the trivial solution or it has infinitely many solutions, including the trivial solution. So either, as an example E, it has only the trivial solution, or as an example F, it may have infinitely many solutions, including the trivial solution. We know that 0, 0, 0 is also a solution to this homogeneous system of equations. So there are only two cases. Either it has only trivial solutions, either it has only the trivial solution, or it has infinitely many solutions, including the trivial solution. Next example, in the following system of linear equations, determine for each value of k, it has a unique solution, infinitely many solutions, or no solutions. The system of equation is 2x1 minus 2x2 equal to 4. x1 plus 3x2 plus 4x3 equal to 14. Negative 3x1 plus 4x2 plus k squared minus a times x3, here k is a constant, equal to k minus 6. So let's first of all write the system of equations as an augmented matrix first. So in the first column, write down the coefficient of x1. I have 2, 1, negative 3. In the second column, write down the coefficient of x2. I have negative 2, 3, and 4. In the third column, write down the coefficient of x3. I have 0, 4, k squared minus a. In the last column, write down the constants. 4, 14, and k minus 6. That's an augmented matrix for the system of linear equations. Next, we try to determine the number of solutions. Based on this rule here, in order to determine the number of solutions, we must write an augmented matrix in the form of reduced row echelon form or row echelon form. Either reduced row echelon form or row echelon form. And since in row echelon form there are less calculation, since writing the matrix in row echelon form has less calculation, so let me reduce this matrix to row echelon form. Because it has less calculation than reduced row echelon form. So for row echelon form, in the first row, first of all I try to make the first non-zero entry to be a leading one. How do I make one here? Here I can simply switch row 1, row 2, and row 3. Row 1 and row 2. Make 1 here. Let me switch row 1 and row 2. Let me simply switch row 1 and row 2. Make 1 here. I have 1, 3, 4, 14. 2, negative 2, 0, and 4. Leave the third row the same. Since that's a leading one, I try to make all entries below leading one to be 0. So here I can multiply first row by -2, add it to the second row. Here I leave the first row the same. 1, 3, 4, and 14. -2 times 1 is -2. -2 plus 2 is 0. -2 times 3 is -6. -6 plus -2 is -8. -2 times -2 times 4 is -8. -8 plus 0 is -8. -2 times 14 is -28. -28 plus 4 is -24. That's the second row. In the third row, I can multiply first row by 3, add it to the third row. So multiply first row by 3, add it to the third row. 3 times 1 is 3. 3 plus -3 is 0. 3 times 3 is 9. 9 plus 14 is 13. Sorry, 9 plus 4 is 13. 3 times 4 is 12. 12 plus k squared minus a. 12 plus k squared minus a. That's k squared plus 4. 3 times 14 is 42. 42 plus k minus 6. That's k minus k plus 36. Next, in the second row, I try to make the first non-zero entry to be a leading one. Here I can divide the second row by -a. So -1/a times R2. Leave the first row the same. Multiply the second row by -1/a. I get 0, 1, 1, 3. Leave the third row the same. I get 0, 13. K squared plus 4, k plus 36. Then for row echelon form, we try to make all entries below leading 1 to be 0. Not above, only below. Try to make all entries below leading 1 to be 0. So I try to make 0 here. I try to make 0 here. In order to make 0 here, I can multiply the second row by -13, add it to the third row. Next, multiply second row by -13, add it to the third row. So I first of all keep the first row and the second row the same. 1, 3, 4, 14, 0, 1, 1, 3. Keep the first and the second row the same. Next, multiply second row by -13, add it to the third row. 0 times -13 plus 0 is 0. 1 times -13 plus 13 is 0. 1 times -13 plus k squared plus 4. I get 13 plus k squared, -13 plus k squared plus 4. Take -13 times 1 plus k squared plus 4. 1 times -13 is -13 plus k squared plus 4. That's k squared minus 9. Next, take -13 times 3 plus k plus 36. -3 times 13 is -39 plus k plus 36. That's k minus 3. So the last entry here is k minus 3. Now before I keep going, let's observe this entry here. This entry, k squared minus 9, it can be factored as k plus 3 times k minus 3. Now let's observe this entry here. Case 1. If k is 3, what do we get? If k is 3, I have, what do I have? I have 1, 3, 4, 14, 0, 1, 1, 3. If k is 3, I get 0, 0, 0. If k is 3, I get 0 here. This entry is also 0. If k is 3, I have 2 non-zero rows, and there are 3 variables. I have 2 non-zero rows, and there are 3 variables. If there are more variables than the number of non-zero rows, then there are infinitely many solutions. Or if k is negative 3, or if k is negative 3, if k is negative 3, then this entry is 0. But this entry is not 0. What do I have? I have 1, 3, 4, 14, 0, 1, 1, 3. If k is negative 3, this entry is 0. So I get 0, 0, 0. Negative 3 minus 3 is negative 6. Then here I can divide the third row by negative 6. I can make 1, 3, 4, 14, 0, 1, 1, 3, 0, 0, 0, 1. This is a row echelon form of a matrix. And here, the last row has 0 equal to 1. Therefore, it's inconsistent. There's no solutions. 0 never equal to 1. In the last row, it has 0 equal to 1. That's impossible. So that's inconsistent. No solutions. So if k equal to negative 3, there are no solutions. If k equal to 3, there are infinitely many solutions. If k equal to negative 3, then there are no solutions. Case 3. If k doesn't equal to plus or minus 3, if k doesn't equal to plus or minus 3, then k squared doesn't equal to 9. If k doesn't equal to plus or minus 3, then k squared doesn't equal to 9. Then k squared minus 9 is not 0. If k squared equal to 9 is not 0, in the third row here, I can divide the third row by k squared minus 9. So in this case, I can multiply the third row by 1 over k squared minus 9, since the denominator is not 0. I can multiply the third row by k squared minus 9, which I have 1, 3, 4, 14, 0, 1, 1, 3, 0, 0, 1. If I take k minus 3 divided by k squared minus 9, I get 1 over k plus 3. That's the row echelon form. That's the row echelon form of the augmented matrix. Since we have the same number of non-zero rows and variables, it has a unique solution. Since in the row echelon form, we have the same number of non-zero rows and variables, it has a unique solution. So if k equal to 3, there are infinitely many solutions. If k equal to negative 3, there are no solutions. If k doesn't equal to plus or minus 3, it has a unique solution. That's an answer to this problem.